21 ECE 212T Control Systems Theory and Applications Unit 2 Part 1 Time Response Analysis. First, let's see the type and order of a system. The order and type of a system are very important to understand how the system behaves and how stable it is. The order of a system is basically the highest power of S in the denominator of the transfer function, or the highest derivative in the differential equation that describes the system. This tells us how complex the system is. The type of a system depends on how many poles are exactly at 0 in the open loop transfer function. These poles at the origin affect how the system responds to inputs like steps or ramps. One important point is that the type can never be greater than the order. It's always less than or equal to order. Understanding these type and order of the system helps us predict the system's steady state error and stability. Let's see an example to find out type and order of the system. Let's consider a transfer function g of s equal to 1 by s square into s plus 1. The highest power of s in the denominator is s square into s, that is 3. So the order of the system is 3. This means there are 3 poles in total. Next, let's see the type of the system. The number of poles at the origin, that is poles where s equal to 0, is 2, because we have a s square term in the denominator. Therefore, the type of the system is 2. So in short, the order tells us the total number of poles and the type tells how many of those poles are at the origin. Next, let's see the standard test signals and their expressions. Test signals are special input signals we use to check how a control system behaves. They help us understand the system's performance, stability, and how it responds to changes. These signals are simple and standardized so that everyone can use the same tests both in theory and in real-world applications. The common types of test signals include step, ramp, parabolic, and impulse signals. By applying these test signals, we can predict and improve system behavior effectively. Next, we are going to see different types of standard test signals. So, as we already told, we have different types of test signals: step, ramp, parabolic, and impulse. Step signal is a signal which jumps suddenly from 0 to 1 at time 0. Mathematically, it's 0 before time 0 and 1 after time 0. It's used to check how the system reacts both immediately, that is transient response, and in the long run, that is steady state response. Next is ramp signal. The signal increases steadily and linearly over time, starting from 0. Mathematically, it's 0 before time 0 and equals to time after 0. It helps us see how well the system can follow a continuously changing input. Parabolic signal increases with the square of time, meaning it grows faster than the ramp signal. Mathematically, it's 0 before time 0 and equals t square by 2 after time 0. It's useful for testing how well higher order systems respond. Impulse signal is a very brief, idealized signal that happens at a single instant with an area of 1. It's 0 everywhere except at time 0. This signal helps us understand the system's dynamic behavior and how it reacts to sudden changes. Next, we have responsive first order system for different types of test signals. First, we are going to see the responsive first order system for step input. General transfer function of first order system is given by h of s equal to y of s by u of s, that is equal to k by tau s plus 1. Unit step input in the Laplace domain is 1 by s. So we can find the response in S domain, that is Laplace domain, equal to y of s equal to h of s into u of s. So that will be equal to k by tau s plus 1 into 1 by s. So y of s equal to k by s into tau s plus 1. Now, to find out the time domain response, perform the partial fraction decomposition. So y of s can be written as a by s plus b by tau s plus 1. By solving for constants a and b, we can get a is equal to k and b is equal to minus k. After substituting the value of a and b and by taking the inverse Laplace transform, the response in time domain is given as y of t equal to a plus b into e raised to minus t by tau. So, after substituting a and b, we can get y of t is equal to k into 1 minus e raised to minus t by tau. For gain k is equal to 1, the response y of t is equal to 1 minus e raised to minus t by tau. So, at t equal to 0, y of t will be equal to 0, and as t approaches infinity, y of t will be equal to 1. So we can represent the response of first order system for step response as shown in the figure. In the same way, we can derive the response of first order system for ramp, parabolic and impulse inputs also. So for the response of ramp input, we can get y of t equal to t minus tau into 1 minus e raised to minus t by tau. The response of impulse input can be found out as y of t equal to 1 by tau e raised to minus t by tau. And for the parabolic input, y of t will be equal to t square by 2 minus tau t plus tau square into 1 minus e raised to minus t by tau. Next, we are going to see second order general transfer function and damping ratio. The general second order transfer function is given as g of s equal to y of s by u of s, which is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. In this equation, omega n is the natural frequency and zeta is the damping ratio. The damping ratio determines the nature of the system's response. It is measure of how oscillations decay in a system. Based on the damping ratio, that is zeta, we can have different types of system. So depending on the value of zeta, we have four types of systems. When zeta equal to 0, the system is known as undamped system. When zeta value is in between 0 and 1, the system is known as underdamped system. When zeta equal to 1, it is a critical damped system. And when zeta is greater than 1, that is known as a overdamped system. Next, we are going to see the response of undamped second order system for step input. So the general transfer function is given as g of s equal to omega n square by s square plus omega n square. So this g of s can be obtained by substituting theta equal to 0 in the general transfer function of second order system. So when we substitute theta equal to 0 in omega n square by s square plus 2 theta omega ns plus omega n square, we can get the transfer function for the undamped second order system as omega n square by s square plus omega n square. So the step input, unit step input u of t will be equal to 1 and the Laplace transform of the unit step input is equal to 1 by s. So we can find out the output response y of s by multiplying g of s, that is transfer function, into the u of s, that is the Laplace transform of input. So that is y of s is equal to omega n square by s into s square plus omega n square. So if we use the partial fraction decomposition to find out y of s, we can get omega n square by omega n square into 1 by s minus omega n by omega n square into s by s square plus omega n square. So in time domain response, we can get it as y of t equal to 1 minus cos omega n t. So we can see if our input is step input, that is given as r of t, our output will be a as shown in the second figure, that is c of t, and the response will be oscillatory as a cosine wave. In the same way, we can derive the response of second order system for step input for other damping conditions also. So if we consider the underdamped system, that is theta value lies between 0 and 1, we will be getting an oscillatory response with decaying amplitude. So y of t will be equal to 1 minus e raised to minus theta omega nt into cos omega dt plus theta by root of 1 minus theta square sin omega dt, where omega d equal to omega n into root of 1 minus theta square. For a critically damped system, that is theta equal to 1, fastest non-oscillatory response can be obtained. So y of t will be equal to 1 minus e raised to minus omega nt into 1 plus omega nt. For overdamped system, that is theta value is greater than 1, we will be getting a non-oscillatory response with slower convergence. So here y of t will be equal to 1 minus lambda 2 e raised to lambda 1 t minus lambda 1 e raised to lambda 2 t divided by lambda 2 minus lambda 1, where lambda 1 is equal to minus theta omega n plus omega n root of theta square minus 1 and lambda 2 is equal to minus theta omega n minus omega n root of theta square minus 1. For undamped system, that is theta equal to 0, oscillatory response with constant amplitude can be obtained. So that is y of t equal to 1 minus cos omega nt. Thank you.